Good evening, everyone. My name is Andrew Fracknoy. I'm the Emeritus Professor of Astronomy at Foothill College, and it's a pleasure for me to welcome everyone to this special lecture in the 22nd year of the Silicon Valley Astronomy Lectures, where each time we bring you a distinguished astronomer talking about what's happening at the very frontiers of our understanding of astronomy. These lectures are co-sponsored by the Foothill College Science, Technology, Engineering, and Math Division, by the SETI, the Search for Extraterrestrial Intelligence Institute, by the Astronomical Society of the Pacific, and by the University of California Observatories, which includes the Lick Observatory in San Jose. We're delighted tonight to welcome a guest who's new to our roster, Dr. Jim Bell, and I'll say more about him in a second. But I want to remind everyone that because of the large audience we have on YouTube, we're not able to take questions directly, but we ask you, if you have questions, to email them to the address astronomy@foothill.edu. That's astronomy@foothill.edu. And Dr. Jeff Matthews will be curating those questions and asking them on your behalf at the end of the talk. Well, now let me introduce our guest. Dr. Jim Bell is a professor in the School of Earth and Space Exploration at Arizona State University. He's an astronomer and planetary scientist who's been involved in solar system exploration using data from many different instruments: the Hubble Space Telescope, Mars rovers, Voyager 2, orbiters sent to Mars, to the moon, and several asteroids. His research focuses particularly on the use of remote sensing images and spectroscopy to assess the geology, the composition, and mineralogy of the surfaces of the planets, moons, asteroids, and comets with which we share our solar system. He's the author of many popular science books, including Postcards from Mars, The Space Book, The Interstellar Age, Discovering Mars, a new one about the history of Mars exploration, The Ultimate Interplanetary Travel Guide, that's a wonderful title, and Hubble Legacy. Dr. Bell was the president of the Planetary Society from 2008 until 2020, and he received the American Astronomical Society's Carl Sagan Medal for public communication in science. There are few people as good at conveying the excitement of modern planetary research than our guest tonight. So it's an honor for me to introduce Dr. Jim Bell. Go ahead.
Wow, that was awesome. It's so great to be here. Professor Fracknoy, I mean, one of my heroes in public communication science. Heard you speak a number of times. It's great to be invited to participate in this event that Foothill and others helped to put on. I used to live in the Bay Area, close to Silicon Valley. I was a postdoc at NASA Ames, Moffett Field, and still a lot of friends up there. And just great to be able to participate in this series and to share some of the really amazing results coming from rovers on Mars. So, should I share my screen? What do you think? Is that good? All right. Let's see. See if we can get Zoom to work properly. All right. First of all, you have to tell me, are you seeing my screen? Yes. And does it fill the screen? It's good. All right. Great. So this is going to be a journey. This is going to be a primarily photographic journey, covering the work that has been done, the results that have come from, the amazing vistas that have come from 4 Mars rovers that I've been fortunate enough to be involved with: Spirit, Opportunity, Curiosity, and Perseverance. I've been a member of or leader of the imaging team on these rovers going back to their first landings back in 2004. So we'll talk about that. And Andy mentioned Mars exploration. there have been, this is a great graphic from Planetary Society, by the way, Jason Davis and others helped put this together. 47 missions, 47 missions launched to Mars going back to 1960. And 8 different nations or organizations, like the European Space Agency, for example, have launched those missions. More than 40% of them have failed, almost half of them have failed. So it's tough, right? Mars is relatively close to us in the solar system. This is partly why we send so many missions, but it's a hard thing to do. But of those that have succeeded, there have been 10 successful landers or rovers on the surface of the planet. Here's a graphic showing all of them. 2 of them called Viking, 2 of them called Mars Exploration Rover, Spirit and Opportunity, Mars Pathfinder Rover, Phoenix Lander, Curiosity, Insight, Perseverance, and Tianwen-1, and the Zhurong Rover. And all of these, up until earlier this year, were NASA missions, and the Chinese Space Agency just became the first other country besides the US to successfully land on Mars. And the European Space Agency will try very soon, the next Mars launch opportunity, to land their own lander and rover on Mars as well. So it's a popular place. There's lots going on. And I can't talk about all of this, but I'm going to talk about the ones that I've been directly involved with. And that is, oops, let me go back. Go back. All right. Well, I'm going to talk about the ones that briefly flashed up on your screen. So it's a story about Spirit, Opportunity, Curiosity, and Perseverance. Partly a story about them, but it's also the story of this enigmatic planet, our next out planetary neighbor, Mars, 50% farther from the sun than the Earth. We've viewed Mars through telescopes for centuries. Of course, we've been exploring Mars with spacecraft now for about 6 decades. And what we found is pretty spectacular. It's a planet with a thin atmosphere, with a heavily cratered ancient surface, some young surface as well, but much ancient surface. Much of Mars is much more ancient than much of the Earth, based on the craters that we see on the surface. The tallest volcanoes in the solar system occur on planet Mars. Enormous constructs like Olympus Mons here, which is the size of the state of Arizona, where I'm talking to you from this evening. Big river channels that are reminiscent of places like the Amazon River basin. On a planet where the atmosphere today is so thin, water would just boil, your glass of water would just boil off into the atmosphere because the pressure is so low and the temperature is so low. And yet we see rock carved by liquid water preserved on the surface of this planet, telling us it was very different long ago. And then there are even some places like this tiny little area, it's only a few hundred meters across, a few football fields across, where it looks like there might be water seeping out of the subsurface of Mars even today in modern times. So there's certainly subsurface ice, there's ice in the polar caps, there may be subsurface liquid water under pressure, kind of like aquifers as well. It's an enigma, right? It's an enigma because we see Mars today, it's cold, it's dry, it's barren on its surface as far as we can tell, bathed in ultraviolet radiation, no ozone layer protecting the surface, no magnetic field protecting the surface. And so it seems to be an incredibly hostile place. But when we look at the oldest parts of the planet, when we look at those ancient terrains up close with the orbiters, and as I'll talk about, the rovers, landers, and other vehicles, what we see is a place that may once have been much more Earth-like. Maybe not exactly like the Earth. It's 50% farther away. It's most likely always been colder, but certainly warmer and wetter than it is today. And an extreme possibility, a hypothesis that has been posed by a number of my planetary science colleagues, is maybe Mars even had oceans. It's speculative. Not everybody agrees in oceans, but at least lakes and rivers and maybe small seas. Pretty unambiguous evidence, some of which I'll show you in this presentation tonight. So a much more different place than it is today, and much more Earth-like than it is today. And so we ask ourselves then, was it a potentially habitable world? Did life occur there? Did life evolve there? Did life exist there? Does life still exist there in that subsurface, which may be warmer and wetter even today? Right? This is why those 47 missions, right? This is why, because it's close. relatively in astronomical terms, and enigmatic and interesting, and it's a mystery that we can reach out as astronomers and planetary scientists with our robotic avatars and try to solve, which is pretty darn exciting. So it's partly a story about this enigmatic planet, and it's partly a story about some really cool, amazing robot geologists, these avatars that I told you about, Spirit and Opportunity, shown here in the lab at the Jet Propulsion Lab in Pasadena prior to their launch in 2003. You can see they're kind of like a golf cart sized vehicles that have sort of 6 wheels, independent steering. It's a spacecraft, right? Just like a spacecraft in orbit, it has a comm system, power system, a main computer, it has a scientific payload. It's just like a spacecraft, it just happens to have wheels, right? And it's solar powered, just like many orbiters and other spacecraft are out in the solar system. So it's partly about Spirit Opportunity. The story is partly about the follow-on mission, Curiosity, which is kind of the big brother, big sister to Spirit and Opportunity, much larger, the size of a Mini Cooper car, launched back in 2011, landing on Mars in 2012, still operating today. I'll show some of the latest results from Curiosity. And then the most recent dynamic duo on Mars, the Perseverance rover, and the Ingenuity helicopter drone that was carried under the belly of Perseverance and set free to fly on Mars. Pretty spectacular stuff. You notice that Perseverance looks a lot like Curiosity. No coincidence. It's about 90% spare parts from Curiosity. This is how NASA, with its limited budget, could fit that new mission into the cost box, the constrained budgetary box that NASA and all federal agencies are under, of course, especially these days. But using spare parts and modifying some aspects of it, different scientific payload, different mission, as I'll talk about, we're able to get Perseverance launched last summer, 2020, and landed this February, 2021. So I'll show some of the latest results there. Now, these are robotic spacecraft, but they have the power of mobility, right? And that's what differentiates them from the Viking landers in the 70s or other landers that have been to the moon or other places. Mobility. This is what geologists want. When you go out in the field, you don't just stand there and look around. You move around, you climb the hills, you go down into the valleys, you go bang on the rocks, right? So having that rocker bogie suspension system that Spirit and Opportunity have, whoa, that's really loud. Let me lower the volume. This one comes with a soundtrack. Yeah, that's better. And having this very similar capability on Curiosity and Perseverance. This is Perseverance here in the lab, moving at about 4 centimeters per second top speed. So not very fast, but fast enough to get us from place to place. And having that mobility is just an absolutely critical capability that these vehicles have. They also carry these very sophisticated science instruments, cameras, spectrometers, of course, communication systems, power systems, etc. Each of them has had an arm that has an abrading tool or a drill or a coring tool, and a variety of microscopes and other kinds of spectrometers to get at the elemental composition, the chemistry, and the minerals, the mineralogy of the surface. Minerals form and alter in response to environmental conditions, just like on the Earth. So they tell us about those environmental conditions in the present as well as the past. So each rover has had successively more complex instrumentation. Curiosity carries sophisticated cameras, an arm with a drill, spectrometers inside the rover body that can do detailed organic chemistry and mineralogy, and the zappy thing coming out of the hat on top of the mast, that's a laser spectrometer that zaps the rock and pulverizes it and vaporizes it, and you can see the emission spectrum of that vapor, just like astronomers look at the emission spectrum of stars. It's the same thing. It's a hot plasma that's ionized, that's creating these beautiful lines in the spectrum that tell us the chemical composition. So, and then the most modern and sophisticated of them, Perseverance, which has a similar array of spectrometers that are designed to make different kinds of chemical, mineral, and organic measurements. A ground penetrating radar. So not only do we see the surface with the cameras, we can see the subsurface, just like we use GPR on the Earth. An oxygen generating experiment to see if we can, in fact, convert CO2 in the atmosphere to oxygen, and that has been successful. And then I mentioned the Ingenuity helicopter, a little drone, not so little actually, 4-meter wingspan, right? So meter and a half, 4-foot wingspan. So pretty sizable drone. Those blades need to be big and they need to move really fast to lift this thing in that very, very thin atmosphere. So all of these tools carried by our silicon-based friends, because we can't go. So we send ourselves to Mars through these vehicles with their eyes, with their arms, with their sense of smell and the chemistry, with their mobility, their legs, right? One of my colleagues once told me, don't anthropomorphize the rovers because they don't like it. So you have to be careful with that. But we do, right? We project ourselves there. They are a projection of ourselves, which is a pretty cool thing to be able to do until such day as we can go. So where do we send them? We send them to geologically and potentially biologically interesting places, right? Mars is a terrestrial planet. The surface area of Mars is the same as all the continental land area of the Earth. So there's a lot of land. There's a lot of places to potentially visit, and we've been mapping the planet since the Mariner 9 mission back 50 years ago. This past week, Mariner 9 went into orbit. 50th anniversary of sort of this sustained orbital presence at Mars. Many missions have followed on that allow us to map the geology, the composition, chemistry. And the Spirit rover, launched in 2003, was sent to a big crater, a hole in the ground called Gusev, because there's a water story there related to the geology. You can see the big channel flowing out of it. I don't know if you can see my cursor. Can you see my cursor on the screen? Yes, maybe. Anyway, you can see the big channel coming out. Okay, you see the big channel coming out to the south, and was probably a crater lake. There's a water story here about early Mars. Opportunity was sent to a very different place, as you'll see, very flat plains where the story about water is related to the minerals, not the geology. This map from one of my colleagues here, Phil Christensen at ASU, and his team's infrared spectrometer that detects minerals like hematite, iron oxide hematite, which can form in liquid water. So there's kind of a different kind of geology and mineral story for these rovers, and a geology story and a water story for Curiosity, going to another big hole in the ground, Gale crater, which has a big mountain of sediments in the middle of it. We can see this from orbit. The top of the mountain of sediments rises above the rim of the crater. Maybe this entire area was full of these sedimentary rocks, and there's sort of fans and flows that we can see from orbit. So what was that environment like? Let's go down there on the surface. Let's take those amazingly sophisticated tools and see what we can figure out and drill into the rocks for the first time. And then Perseverance was sent to another hole in the ground. Hey, this is a common theme, right? Mars has a bunch of craters, and many of them were lakes when there was a lot of water. And Jezero crater, which is only about 50 kilometers or so across, has a clear inlet valley and an outlet valley, and lots of evidence that it was filled with water. And there's a beautiful delta right at the terminus of this western inlet valley, like the delta at the end of the Mississippi River or the Mekong River, right? Sediments coming down from the highlands, being deposited gently into this shallow water lake, and leaving behind, evidence for whatever was upstream, and maybe preserving evidence for what that ancient environment was like. So each of these missions going after kind of a different part of the water story. Launched on rockets, right? You take this sophisticated, sensitive optical equipment and you put it intentionally on a bomb, and you send it off, and you bite your tongue and cross your fingers and everything else and say, I hope it works. And in the case of all four of these, they launched perfectly. NASA and their partners who launch rockets did just an amazing job sending these missions to exactly where they needed to go. I'm not a rocket scientist in this sense. This baffles me, but it's also just incredible, the accuracy, the pinpoint accuracy that they can get these vehicles off, hundreds and hundreds of millions of miles away. It's just spectacular. Okay, let's dive in. Let's start with Spirit and Gusev crater. And here is a one-slide summary of the mission of the Spirit rover, landing in January of 2004 and driving across the plains of this first explored crater and potential crater lake up into these beautiful hills called the Columbia Hills, named after the astronauts lost in the Columbia shuttle disaster, which happened not long before the mission. And driving up into these hills, over the backside, into this valley beyond, and down to this little area called home plate. 2,210 Mars days this rover lived, and it was supposed to live 90. Its manufacturer's warranty from our engineering colleagues was it'll live 90 days on Mars. 2,210 later, it's a spectacular mission, more than 6 Earth years, almost 5 miles of driving across the surface. It's a nice shot of you may remember, Spirit and Opportunity landed on these airbags, bouncing across the surface, coming to rest, deflating the airbags, opening the flower petals, and driving off into Mars exploration history off of the surface and turning around, taking a picture. I love this picture because you get a sense of, it's not just rocket science, right? It's sewing and welding and gears and cloth. It's just so many skills, so much ability, so much engineering goes into creating these spacecraft and their systems. It literally takes thousands of people, all over the country, all over the world, to put the parts together, to do the design, put the parts together, test it, launch it, and then operate these vehicles. So seeing the equipment that brought the rover to Mars was a very emotional and exciting moment. We very quickly discovered after we landed that we were dealing with a lot of volcanic rocks. We could see these beautiful lava textures on the surfaces here. We were able to image very late in the day with the sun very low, really bring out the texture of the rock, which you can do, and photographers know you do that with low sun angles, right? And lots of evidence, not only in the texture, but in the chemistry and the minerals, that these are garden variety volcanic rocks, not unlike what you would find in Hawaii, the big island of Hawaii, or what you'd find in Iceland erupting from the ground today. Similar kinds of rock called basalt, right? All the terrestrial planets had this very common rock type. The problem was we wanted to go to a lake bed. We thought we were going to a lake bed. We wanted to find lake sediments. Tell us about ancient water on Mars. Instead, we found a bone dry uppermost surface covered in volcanic rocks. Of course, it's because that early watery history was a long time ago, 2, 3, 4 billion years ago. And lots has happened since then, including subsequent volcanic eruptions that appear to have covered many of these putative lake sediments. I promised I'd say a little bit about chemistry and mineralogy. I'll just show one of these. I call this a squiggly line plot. Just so you know, it's not just about the pictures, right? We have spectrometers on all of these rovers that can give us details about the elemental chemistry and the mineralogy. And these are some of the kinds of plots that they produce. So in the papers that the team writes that present the scientific results, yes, we have pictures. Yes, we talk about the geology and the landscape. But these kinds of instruments, these detailed squiggly line spectrometer instruments, are what give us the deep understanding of the science, the chemistry, the mineralogy, how things have changed over time. What are the parent materials? What are the weathered materials? What was that weathering environment like? And here is where, in these kinds of plots, is where we started seeing sort of the first evidence of, hey, you know what? There are some water formed and water altered materials here. It's not just bone dry volcanic rock. So we were compelled, however, to get out of those volcanic plains and to climb those mountains. And this panorama, which is coming in very quickly here, shows the sort of mountaineer's view. The rover has climbed up 50, 100 meters or so above the plains. You can see it's a windy place. You can see these sand dunes up there. And it's kind of like, yes, we've made it to the top. Here's our Mount Everest panorama, we called it, the highest point around. And here, above all those garden variety lava plains, is where we really started seeing a lot of interesting things in the chemistry and the mineralogy. Somewhat dangerous places as well, huge sand dunes piled up against these these mountains. There's lots of sand on Mars. On Earth, most sand is quartz, right? SiO2. Mars doesn't have much quartz. It's a basaltic planet. If you've ever seen a black sand beach, maybe some of you have been to a black sand beach in Hawaii or Iceland or other places. Mars is like a planet of black sand beaches. And the mineral olivine, which is a major component of this sand, many people know olivine as the gemstone peridot. That mineral is just as hard as sand, as quartz sand on the Earth. So it's just like quartz sand on the Earth. It's hard to break it down. It accumulates, it piles up into dunes, into these features, which are rover death traps. We have to be really careful with these rovers. We can't drive into there because it's soft and we'll spin our wheels and we will literally get bogged down and stuck, and that'll be the end of the mission. But they're beautiful to photograph, and we could stick the arm out just into them and get some chemical and mineral measurements because this is a very common material on Mars, so we want to learn a lot about it. So a few years in to the mission, I'm going to show a time lapse here of images from the front hazard cameras, wide angle lenses. You can see the wheels here. A few years into the mission, the right front wheel stopped spinning. That motor stopped working, and it locked that wheel. And so we couldn't drive forward anymore because it would try to push that wheel through the sand. So we had to drive backwards. And you can see the wheel is locked there in this animation over the course of several sols on Mars. And you can see that because we're dragging the wheel, we still have mobility, slower, but we're dragging that wheel backwards now. It is creating a trench. And this was one of these serendipity things, right? We didn't want the wheel to get stuck. We didn't want to be creating this big trench. But what happened was the trench dug up minerals that we would not have seen otherwise. Dumb luck, kind of, right? Sulfur-rich minerals, hydrated sulfur-rich minerals, silica-rich minerals, hydrated silica-rich minerals, the kinds of hydrated minerals that you find around volcanic vents on the Earth that have interacted with water, steam and water. Hey, you know what? There was groundwater here associated with these volcanic eruptions, and it was forming these different kinds of rocks and minerals. The one place where we went to at the end, we saw this little circular structure here, and we called it home plate because it kind of looked like the home plate on a baseball diamond. Whole bunch of baseball nerds involved in the rover missions, so we're always thinking about baseball themes. And this place we could see from orbit. This is an orbital picture from the Mars Reconnaissance Orbiter HiRISE instrument. We could see it, and we could see it had layering on it. We could see its mineralogy looked a little bit different from orbit. And in the midst of this volcanic terrain, we were able to get the rover out onto this feature, drive up and across it, and look at it, layered deposits and minerals, and tell a story. You can see how much the yellow path is all these different times. The black dots are the different Mars days. We spent a lot of time. We spent 5 years. We spent 5 Earth years just at this place, because the hypothesis is that maybe it really was a hydrothermal vent system. Maybe it was something like Grand Prismatic Hot Springs in Yellowstone Park, for example. Volcanic heat coming from below, creating melting ice, or creating an environment that could be conducive to liquid water, creating the minerals that form in such environments, many common sulfates and silica minerals that we see in places like Yellowstone, we found there in Gusev, and really telling us, yes, you know what? Yellowstone is a habitable environment, right? Lots of microbes are responsible for the colors that we see here in the water. And holy cow, a similar kind of place may have existed in this crater on Mars. And so that was super exciting to be able to tell that story with the Spirit rover. And the mission actually ended right here. It ended for a variety of reasons. The rover was getting old, things were breaking, like the wheel, and these are solar powered Spirit and Opportunity. So we landed with clean solar panels. This is a selfie, but pointing the cameras down, looking at the rover deck. By 2007, more dusty. By 2010, where's the rover? Right? Super dusty. It's all of this settling dust out of the Mars atmosphere. Occasionally the wind would come along and clean us off, and our power would go up. We'd have a new life. But over time, more and more dust. So our power levels are getting lower and lower and lower. And then in 2010, in the spring of 2010, we've accidentally, without even realizing it, ended up over these crusty soils. You can see the crusty soils that the rear wheel is breaking through there as we're driving. And the rover kind of fell through these crusty soils. We had no way of recognizing them. Fell through the crusty soils, spinning our wheels. We couldn't make much progress. Power going down. Couldn't spin our wheels very long every day, and it spelled the end for the Spirit mission. So in March of 2010, you can see the big trench that we're making trying to get this vehicle out. We weren't able to do that. It's frustrating because it's super interesting stuff here for geologists, right? I mean, crazy minerals and layered rocks, and it's like, we got to get out of it. We got to move on, use that mobility. Well, despite a vigorous internet campaign, and maybe some of you participated in, we were not able to get that rover out, and its mission ended in March of 2010. It's still there. We can see it from orbit. Nobody's taken it. The wheels are still on. That mission was incredibly well done for a 90-day mission, but came to an end in 2010. Now, Spirit has a twin, Opportunity, launched also in the summer of 2003 to a very different place, the other side of the planet, Sinus Meridiani in telescopes, Meridiani Planum to geologic mappers, where that rover lasted for 5,111 sols on Mars. A day on Mars is called a sol. And again, was supposed to last 90. More than 14 years of operation, more than 28 miles, a marathon's worth of driving on Mars, setting the current robotic land distance record for off-planet vehicles, and driving around a whole bunch of craters. I'll show you some pictures of them, and including this one, the one that we landed in, called Eagle Crater, because of the golfing theme there. And a small crater, it would be about the size of the auditorium if we were in an auditorium together. And there's the lander in the middle, same airbags, flower petal opening, and we drove off. You see all the tire tracks we made, kind of a mess. But look at on the walls of that crater, these beautiful outcrop rocks exposed in the walls of the crater. This is the first time that we'd seen an outcrop. It was also the first time we'd seen on Mars, the first time we'd seen the ground covered in these little spherical grains, which we started calling blueberries because they're bluer than the surroundings. Just astronomers know red, blue, right? If something is redder, you call it red. If something is bluer, you call it blue. And they're not actually blue, they're actually quite red, but they're little spheres, millimeter to centimeter size, littering the ground everywhere we looked. And this was a puzzle when we landed. It was like we were in an alien planet of some kind. It was really interesting. But that outcrop was super special, right? Outcrop is a holy word to geologists, right? If you go to a party and you say outcrop, a bunch of geologists, their heads will spin around. You get their attention, right? And we'd never seen it up close before on Mars. And we could see it from the lander, right when we landed. We could see it and zoom in on it the best we could. It's still fuzzy because it was 10 meters away or so. So we could, instead of dealing with fuzziness, we could drive over there and get closer so we could get an even better picture right up against it of this outcrop. And we could zoom in as best we can on this stuff, but the cameras are a couple of meters away from the surface, and we can't get the cameras down there except that we carried a microscope right on the arm. So we take the arm and we put the arm down there, and we can zoom in even further and see this now we're hundreds of millions of miles away, zooming in on an individual's layers of an individual rock. And look at that, we can see those blueberries. We can see those blueberries in the rock. So that what's scattered across the surface is popping out of this rock like blueberries coming out of a muffin. Super exciting. We also saw these beautiful layered rocks, these little cross beds, geologists call them, telling us about sand and reworked by water, shallow water wave action going back and forth, preserved in the sandy sediments on this place on Mars. So super, super exciting. We kept going to bigger and bigger craters. Endurance Crater, the next one we went to, this is about the size of the Rose Bowl football stadium. And we can see these beautiful layers off in the distance. A bunch of geologists on the team, let's go down there. Let's use mobility, get inside the crater. Not easy to do, steep slopes. You can see the steep slopes here. So we had to do a whole bunch of testing. Turn the sound on this. Here's the test rover at JPL, testing going down into over some of the slopes. and this has been balanced for the gravity of Mars. And Randy here is going to spot the test rover. That's not good, right? It's not good because Randy is not on Mars. We can't do that. That would be the end of the mission. There's nothing we could do. So they did a whole bunch of testing and figured out, hey, let's come at, I'll speed it up here. Let's come at it at an angle instead of straight on. Watch this. Okay, we come at it at an angle. And of course, because they're engineers, they get the angle to 1/10 of a degree, you know, with all this practice and all that kind of stuff. It was great. And so having the test vehicle on the Earth allowed us to, you know, do things like take risks, calculated risks, going down into the crater. So here we are poised on the edge with our giant shadow at the low sun, pretending to be a monster truck. Now we got to be careful because at the bottom of that crater, more deadly sand dunes. We don't want to slide down into that because that'll end the mission. Beautiful to look at. And this is a false color composite, infrared false color composite. Beautiful to look at, really interesting chemically and mineralogically and geologically, but death traps for a rover. So we had to be really careful, but they did it. The engineers got us down there. And now here we are inside the bowl of that crater, looking, you know, panning around, looking at these beautiful layers that are from the subsurface of Mars, right? And we see these beautiful sand dunes, layered, interacting with each other, interacting with water, altered. You see those blueberries all throughout these layered rocks. And we think they're the same kind of rocks that we find in places like desert Southwest on the Earth, where water is percolating through these rocks, precipitating iron and other iron-bearing minerals like hematite. We found a lot of that mineral hematite in these little blueberry grains, the stuff that we saw from orbit that got us down to this place. Turns out the carrier is these little grains of altered, water-formed, water-altered minerals embedded in this rock, which was saturated with water at one point in the deep past. Keep going to bigger craters. Bigger craters allow us to probe deeper into the subsurface, right? And we'll zoom in here to Victoria Crater, where we spent a year, an Earth year, with this vehicle. Here's the rover seen from orbit. You can see all the rover tracks there. We can see the camera mast. We can see the shadow of the camera mast from orbit. We have a great spy satellites at Mars, by the way, helping us do geology and helping us decide where to drive and what to do. Take that view now down to the surface, and this is what we see down there. And I put a CG model of the rover in just for scale, because it's really hard to tell the scale. Many of us don't know what a rover looks like size-wise, so it's hard to deal with. So here's another version with some Buzz Aldrins. Many of us know what the size of Buzz Aldrin is. And so here's Buzz for scale at some of these places. Pretty dangerous place, pretty exciting place to be. Imagine hiking around here, scaling some of these cliffs. Pretty dangerous place to be driving a remote control autonomous vehicle. Very careful driving. You don't want to drive off the cliff, because that'll be the end of the mission, right? And we did get pretty close to characterize many of these layers. A little bit of a postcard photo album from that year, exploring these just amazing, incredible vistas, beautiful layered rocks, deep tens of meters down into the subsurface, again, loaded with those kinds of water-formed minerals. That aqueous history, that watery history, wasn't just where we landed. It's extensive throughout this area. So it wasn't just a flash in the pan. Here's a rock hammer for scale. You can see these just beautiful cross beds in there again. You can see some of what we think is the original surface before the crater came in and disrupted everything. This is a big asteroid or comet, hits the surface, fractures everything, excavates, throws this pile of stuff out, but digs up from the subsurface and exposes the subsurface for us. So just really some of the most amazing off-planet landscapes that I've ever experienced. By 10 years in, we got to even the biggest crater that we've been to, Endeavour Crater, which is about the size of the Washington, D.C. metro area. So it's a pretty big sized crater. We were able to get up there and travel along the rim of this even larger crater, more energy, more excavation, more alteration. And we found beautiful evidence of veins, water-formed veins of minerals like carbonates that are traveling, carrying minerals through these watery veins, clays deposited on the surface, all signs of that watery past, all signs of an environment that could support liquid water on and close to the surface. an environment much more Earth-like than Mars is today. Like Spirit, Opportunity's mission came to an end in 2018. A giant dust storm, you may be familiar with the fact that Mars has these giant dust storms occasionally. Giant dust storm darkened the skies, literally blotted out the sun. And these are solar-powered spacecraft, right? So you blot out the sun for days and days at a time, power drops off, and that's the end of the mission. So in June of 2018, we took our last images, which were part of this big panorama that we were taking. But that was the end. There wasn't enough power to stay alive, run the heaters at night, where it gets down to minus 110 degrees Celsius, to run the transmitter, etc. So Opportunity's mission came to an end in June of 2018. Pretty cool though, lasting much longer than they were supposed to, and providing both Opportunity and Spirit feeding into what Curiosity, the next rover launched in 2011 and landed in 2012, was able to do. I'm not going to show that, but you can go watch the descent animation. It's just too loud and I can't control the volume. But suffice it to say, we used a different landing system, sky crane landing instead of the airbags, different power system, nuclear power like Voyager, like Galileo, like Cassini, nuclear power instead of solar power, so we aren't as susceptible to dust. Landing safely on the surface in August of 2012, and you can see the rover tracks driving away. Here's the view from the ground. Look at that. The rover tracks just sort of start. They start from that point in the upper right. It's like we came from the sky, right? Boom, and then you drive away. And this mission's still going. And I'll update you on some of the latest results. We've driven across this part of Gale Crater, landing in the ellipse here on the relatively flat part, and driving to that giant mountain of sediments over the past almost 10 years now, nine years and change, across the surface, winding our way through these dangerous sand dunes, and now starting to climb up the slopes. Right when we landed, we found beautiful evidence of conglomerates, rounded pebbles. Those rivers coming off of the walls of the crater were carrying a lot of sediment, carrying probably ankle to knee deep rivers flowing across the ground in this area, rounding the rocks. Super exciting, just right when you land, to see that evidence of that watery past. We've seen lots more evidence across the floor of the crater. Beautiful, fine layered deposits. These aren't sandstones, these are mudstones, right? Mud forming these layers in shallow to deeper parts of an ancient lake, which was getting to hundreds of meters to kilometers deep in places. A significant amount of water for a significant amount of time, producing significant sediments that preserve evidence of that watery environment. We're able to drill for the first time with Curiosity. And so we drill into the rock. And when you drill into Mars, red Mars becomes gray Mars, right? The redness is partly because of the dust, partly because of alteration and oxidation over time. But just under the surface, there's a lot of pristine, grayish, unoxidized, unaltered materials that we're able to uncover. We see lots of evidence of veins and fracture-filled, mineral-filled fractures, similar to what we were seeing at the end of the Opportunity mission, but all over the place in Gale. Of course, the place is fractured because it's a crater, but there was a lot of water going through this system, both in the lake itself and in a groundwater system. All of this led to some very early discoveries, exploring habitability, discovering that this was a habitable environment by the way we define it: liquid water, heat sources, organic molecules, primitive ones. We don't see any organic molecules that are like what's in us, but we see primitive ones like we see in meteorites, and they're the starting blocks of amino acids and other more complex organic molecules. We found them there on Mars. And writing these papers, again, just like the previous rovers, lots of squiggly line stuff went into this. You can go look at Science Magazine and get a lot of squiggly lines if that's what you like. That's where a lot of the deep science is that gives us the details of the chemistry and the mineralogy. Well, now it's almost 10 years on Mars, right? And we've got more than 30 drill holes now. All these materials, as we're going, especially as we're going up the geologic cross section, drilling into them, making detailed measurements of the chemistry and mineralogy, drilling and making measurements, just like we would do if we were out on a field trip with collecting samples, or if we were to send our graduate students out on a field trip to collect samples out in the field and then bring them back to the lab. Except the lab is with us with Curiosity. Problematic wheels have been getting heavily damaged. These rocks, many of these rocks are extremely tough, sharp, angular. They're causing dents and absolute rips in the wheels. So the Curiosity has had to become a dune buggy and try to find the sand and drive more on sand as much as possible, but not super deep sand, because we still have that same rocker bogie suspension kind of system. And it's not treads like a bulldozer would have, it's wheels. So we can't get in super deep sand. But if we can stay on softer material, it does less damage to the wheels. That's something that has been pragmatic. So now we started climbing these slopes. Again, more spectacular vistas. You can see these beautiful layered rocks, these sedimentary rocks, that giant mound of sediments in the center of the crater. And just some, especially over the past few months, beautiful, beautiful vistas of these landscapes, these layered rocks. You see these fine sandstones and mudstones. We're starting to head up a very narrow slot canyon here pretty soon. The views are just going to get better and better. If you're a fan of interplanetary photography, follow along on this website for the mission updates. Absolutely spectacular stuff. I have to show some art, right? And it's pretty cool rover art. I like this one, kind of Andy Warhol. And then, of course, Rover classic, both Spirit, Opportunity, and Curiosity portrayed here. I love what the public does with these things. It's just absolutely spectacular. Okay, so what's the next step? We started in '97 with the little laser printer size Mars Pathfinder rover. We graduated to golf cart size Spirit and Opportunity. We graduated to Mini Cooper size Curiosity. The next step is pretty obvious, right? This is the part where if we were together, maybe you'd laugh and I'd hear you laughing at my jokes. So I'm going to pretend you're all laughing at my jokes. But anyway, so that's not Optimus Prime. The next step, Perseverance, 90% spare parts from Curiosity, fitted in the cost box. Don't have to build everything from scratch. Let's get another mission up there to do some incredible things at another interesting landing site. So final part of the talk here, talking about what Mars 2020 mission launched in 2020 is doing, Perseverance rover. We're exploring the geology. We're looking for signs of that habitability that I've been talking about, and biosignatures, right? We don't expect to find fossils. Honestly, we don't. Fossils only have come recently on our own planet, only in the last 500 million years, the last 10% of our planet's history. Do we have a fossil record? Life before then, which life started very early, soft-bodied, single-celled, multicellular clusters, right? But that early life formed textures like stromatolites on our planet. This is what Precambrian geologists study on the Earth. So we're looking for similar kinds of textures. We're looking for similar kinds of chemistry, similar kinds of mineralogy, biosignatures in the geologic record. Unlike Curiosity, yes, we can drill, we can core, we can capture what we drill and put those captured drill cores into sealed containers that we hope to bring back to the Earth in the future, not by Perseverance itself, but by future mission I'll talk about briefly. And that's all in preparation for sending people there. So launched last summer, summer of 2020, landed this February. We are now 265 days into our planned one Mars year mission. So 690 days, Earth days or so on Mars. That's the plan. We're about a third of the way into that. If things go like they have with previous rovers, maybe we'll last a lot longer. But the goal is to collect a bunch of samples, cache them, and place them on the surface for a future mission I'll talk about in a minute to come get. So Perseverance was number 9, Zhurong, number 10 shortly afterwards this past spring. And here's where the 10 landers have gone. And I mentioned that we landed in Jezero Crater with Perseverance because of that beautiful delta seen in a false color infrared mineral map. And we landed very close to the delta in the smooth terrain right in front of the delta. I mean, again, the accuracy of this bullseye to send this vehicle across interplanetary space and land right next to the thing that we wanted to study. that delta. Absolutely spectacular. So we landed very close to it, and we've driven over the past 265 days on Mars across this path around some very dangerous sand dunes, looking for places to sample, looking for places to collect those first samples. Here's our panorama of our landing site. You see the same kind of scour marks that we saw for Curiosity, because the same retro rocket sky crane system, spare parts, brought us to Mars, just like Curiosity did. And so that was pretty exciting. We landed in a relatively safe spot, a place we could drive, not in the middle of sand dunes, not on some crazy slopes. This is all good. Our engineering colleagues did their jobs. Our cameras can take false color images just like previous cameras. So we use the filters in the infrared and the ultraviolet to characterize the differences in color and relate them to chemistry and mineralogy. These are cameras, not spectrometers, but these help us point the spectrometers, put them on the most interesting places, because we can't do the spectroscopy everywhere. We have to be very selective. So we landed pretty close to that delta. Here's where actually we landed up here, and we're only a couple of kilometers away from the front edge of that delta. And the cool thing is we could see it. We could use the zoom cameras that we control here at ASU and see the front of that delta from a couple of kilometers away. And we can see these beautiful layered rocks. We can see these sediments that we know are there from orbit. And now we're on the ground looking at these sediments from this oblique view. We've landed, right? We're looking at the place through our landed eyes. And one of the coolest places we've seen so far is this butte here, which is called Kodiak. And I have a picture of it here. There we go. That's what it looks like from orbit. It's that little knob right there. And that's what it looks like from the ground. And this has been super interesting because we've timed the imaging when the sun is just rising behind the rover. It lights up the front end of these beautiful sediments. And we see these spectacular layered rocks. And we see boulders preserved in the layered rocks. And we see cross beds and, interesting cross-cutting relationships and stratigraphy, right? And actually, we got our first scientific results of the mission just published last week in Science Magazine. We had the picture on the cover of Science Magazine. It's like the cover of Rolling Stone for scientists, right? I mean, getting on the cover of Science Magazine, that's a big deal. And we're super excited about that. But we basically, it was a hypothesis from orbit. This looks like these are delta sediments. And we get down on the ground and we verify that. Look, indeed, it is delta sediments, but it's a more complex history than that. These big boulders in the upper layers. So yes, there was that gentle sedimentation, that gentle building up of the stratigraphy, but there was also violent episodes of intense flooding that were moving big boulders and rounding them, rolling them across the landscape, coming down from the ancient highlands above the crater walls. So really interesting story there. We just started telling part of it. Meanwhile, right, we brought Ingenuity to Mars under the belly of Perseverance. We dropped it on its surface, and in April we backed away, spun up the blades, and Ingenuity became the first powered vehicle on another planet, first powered flight off Earth in April of 2021. Here's the historic first flight. The place where we took off has been named Wright Brothers Field, informally named Wright Brothers Field, in honor of the first powered flight 100 years earlier, more than 100 years earlier on our own planet. A very simple first flight, right? Just up, do a little twist, let the wind bob you around a little bit, take a whole bunch of telemetry data, measure what's going on, how the rotors are working. Are we spinning fast enough? Did we lift at the right rate? What kind of resistance are we getting to the wind? And then set down back onto the surface. So we took these movies with our Mastcam Z cameras that we run here at ASU, and we took a whole bunch of them in April and May. Here's a high video rate slow-mo replay of the landing from one of the flights. Stuck the landing. So the engineers learn a lot about the landing systems, the flight systems, and all that. Here's a heavily processed version on the left. The helicopter flew out of the scene and then flew back and brought a whole bunch of dust with it when it came back. And so the atmospheric science folks are super excited now because we're basically making a little mini dust devil, a little mini dust storm with the helicopter. So we've now intentionally done some experiments to use the helicopter as a source of a known wind source. and measure the properties of dust lifting on Mars. So we turned it into an experiment. And the helicopter itself has its own cameras, and it's doing scouting now for the rover. This is a time lapse. The sun is right overhead because these flights have been right about at high noon. So there's the shadow of the helicopter, and we send the helicopter over places where the rover can't go. But we want to scout them out ahead of time. We want to learn about the context of those places relative to those places where the rover can go. So they really started to work together, which was the whole goal of having a drone in the first place. So it's really the start of multi-robotic interactions on another planet, and lots of cool stuff here, lots feeding forward to the eventual quadcopter that's going to fly on Titan in the 2030s, and hopefully future copters and other drones that'll fly on Mars in the future as well. So I mentioned we have a coring tool, not just drilling, but coring. And so we collected our first core, did our first coring in these flat-lying rocks that we could see around the landing site. You can see the little hole there. Here's a zoom up of the hole with the little dots are from the laser zapper, creating little zap pits to measure the composition as we went down. So this was our first coring activity, super excited, but the core tube came up empty. This was disappointing. What happened? Where did it go? We drilled the hole, this core sample there, and it turns out the rock is very soft and crumbly, and most of the core is right here in the little mini cone, little cinder cone that was made around the hole. But that volume is about the right volume to be the core. It got pulverized. It turns out the rock is much softer than we thought. We have an atmospheric sample in that tube. It got sealed, empty. So we have an atmospheric sample. We wanted to collect some atmospheric samples anyway, so we got that. And these rocks are really curious. We have to figure out how to sample these rocks, but they're not the hard rocks that we thought they were going to be. So there's a puzzle here related to weathering and alteration that we have to solve. What we did in our second coring attempt, we did find a hard and potentially volcanic rock called Rochette. And here's a zoom up of it. We were able to abrade into it and demonstrate, yes, it is as hard as we think. And then we were able to drill and core into it. Here's a before and after of the core hole. And lo and behold, we captured the core this time. It got into the core sample. And here's a picture on Earth of that exact sample tube. And so it was taken out. The rover brings the arm to a carousel that brings the sample tube into the rover, into a little sample processing facility in the front of the rover, where that tube is now safely tucked into a tray, ready to eventually be dropped onto the surface and picked up by a future mission. So we actually then went back and got a second sample from the same rock because we want some redundancy. We want to assess the variability of that rock. So now we have a number of our first samples, literally in the can inside the rover. So we know the sampling system works. This is a huge demonstration everybody was nervous about. Very complex system. There's a tiny little robotic arm like a Tyrannosaurus arm inside the rover that moves stuff around from station to station, does the hermetic sealing, does photography, etc. So that's super exciting. So we got our first samples collected in this really interesting layered area, the area with layered rocks that's in front of the delta. So we think these might be lake sediments. We need to test that. We're analyzing the data daily as these images and other measurements come in. And we're going to head back to where we came and loop around. I'll show you the path here in a moment. And Ingenuity is going to head back as well, trying to stay with the rover and continue to scout out these terrains, especially, we can't drive in these sand dunes, but we can fly the copter right over and get all kinds of great information that's better than orbital scale. So we're going to drive back the way we came and loop around, look at areas excavated by this crater, and then head towards the front of that delta. We're going to obtain more samples of volcanic rocks and possible lake sediments, including just this week, we collected we did our fourth coring and collected on Monday our first sample of these layered rocks in this terrain. We're going to collect a second sample in this area any time now this week or this weekend. And so really putting the sampling system to work and starting to stash a collection of these samples inside. And we're going to loop around and get to eventually to the front of the delta. Probably not until spring or summer of next year. It's a slow drive. There's going to be really cool stuff to see along the way, but the delta is our target. Getting to that cliff, that scarp, looking at those layers up close, sampling that material, collecting some of that material, not just the rocks, but we can collect soft material as well, getting it inside the rover and collecting samples for a future mission to bring back to the Earth. So that's what's the future, right? What is the future of Mars exploration? Well, the first step is Mars sample return. Perseverance is the first part of Mars sample return that NASA and the European Space Agency are planning together. These tubes, which are inside the rover now, we're going to collect 20, 30 of them. We've got 42 of them in there. Collect as many as we can over the course of the next few years, and then set them onto the surface, probably in one or more caches. They'll be safe on the surface. They're metallic, they're painted white, they won't get hot. They'll be easy to find. We're not going to hide them. Nobody's going to come take them from us unless we want them taken, right, by a future mission. And a future fetch rover that NASA and the Europeans are designing, which could get launched as early as 26 or 27. We'll go back to where we leave them. We'll pick them up, those samples up, bring them back to its fetch lander, which has a rocket on it, a solid rocket, put those samples into a container on the rocket, launch the rocket up to an orbiter that's waiting to find and receive the sample container, and bring that sample container back to the Earth as early as 2031 or 2032. What could go wrong, right? It sounds simple. Incredibly complex mission. It's in the planning stages right now. Many parts of this and this are being worked by really smart engineers around the world, trying to put this system together and fit it all into the cost box that NASA has to fit everything we do. And so that's the next step, right? Mars sample return has begun with the Perseverance mission. The Europeans will launch their next attempted lander rover. They've tried previously unsuccessfully because it's hard. They'll try again next summer with the launch of their ExoMars lander and Rosalind Franklin rover to Mars. So NASA and ESA have plans for Mars sample return. Of course, the Chinese have amazing, they're the first attempt, successful orbiter, lander, and rover on the surface of Mars. So they've got plans. SpaceX, you've heard many Elon Musk's plans to send hundreds of thousands of people to Mars. They're going to go. Others, what's next in the 2030s? People are going to go, right? Will it be NASA astronauts? Will it be SpaceX employees? Will it be Chinese taikonauts? Will it be some combination of all of those? Obviously, many of us who are big fans of international collaboration hope we can all figure out how to do it together, put our neurons together, put our dollars and euros and yuans together, and that would be best. I'm hoping we can do that. Not clear that we will, but it's happening. It's coming. Getting people to Mars is coming, and I'm really super excited about that. So we've been there to Mars with these robotic avatars, right? And I was reminded when I saw our first sunset view from Gusev in 2005, Charles Darwin's quote, right? How great would be the desire in every admirer of nature to behold, if such were possible, the scenery of another planet, 1839, right? 150, 160 years later, it is possible. We are beholding the scenery of another planet, and pretty spectacular, right? Beautiful time-lapse sunset and Gale Crater from the Curiosity rover in 2012. And then just a week and a half ago, our first sunset view from Perseverance in Jezero Crater. And I'm, looking forward to seeing this sunset view. This is a clip from just a spectacular short film called Wanderers by Eric Bernquist. You can go to Eric's website and watch it. It's only a couple of minutes long, but it puts people out in the solar system using real pictures like this, taken by robotic missions over the past decades, and just imagines this future that's coming over the next decades to centuries when people will be out there and enjoying these sunset views on their own. And we're reminded that the real voyage of discovery for us today is not in seeing these new landscapes, but in having new eyes. And in our case, it's robotic eyes, right? We project ourselves out through these amazing avatars. We wish we could go. We will go eventually. I'm trying to stay fit, eat well, if I can make the trip. I want to come back to the Earth, by the way. Earth is my favorite planet. I've lived here most of my life, and most of my friends are from here. So I definitely want to come back, but I would love to go on a trip. In the meantime, we live vicariously through our avatars, right? And you can follow along with learning about what Spirit and Opportunity did, learning what Curiosity and Perseverance and Ingenuity are doing today, and learning what the future is coming in Mars exploration. I hope you've enjoyed this series of postcards and postcardy movies, tweets, and Instagram posts from another planet. And I'd be delighted to take questions. Thanks.
Excellent. And thank you so much, Dr. Bell. It's wonderful to have this kind of guided tour, because even those of us who have seen a few of the pictures don't have that behind the scenes feel that you're able to convey. That was really fascinating to see. Let me now introduce the astronomy professor at Foothill College, Dr. Jeff Matthews, and he has been curating the questions that have been coming in. Let me remind our current viewers, our live viewers, that the questions can be asked at astronomy@foothill.edu. And I'm going to hand things over to Dr. Jeff Matthews for the question period.
Thank you, Andy. And thank you, Dr. Bell, for your talk this evening. That was fantastic. I would also like to thank all the people who have been emailing in questions. I've been trying to kind of group them up. There's been some repeats here. Or people asking similar questions. And so we'll start off with several questions sort of about the rovers themselves. So here's one from Chris asking, saying, engineers were so happy when Martian winds cleaned off the dust that built up on the panels. Did they ever consider having some sort of fan or pressurized gas on the rovers to physically clean the panels?
Yeah, I loved it. I get this question every single time I give this talk. I love this question. It's a great question. It's an obvious question, right? Why don't we just bring a wiper blade or whatever, right? And the reason, maybe it's not obvious, right? The reason is not because it's hard to build a wiper blade. The reason is not because it's hard to carry a spray can of air, right? That's not the reason. The reason is it's a zero-sum game. And our engineering colleagues, we talked to them about this. Aren't the panels going to get dusty? They said, yeah, we can do something about it. We'll build you a wiper system, right? However, we can only send so much mass in that rocket. So what do you want to take off? You want to take off the spare transmitter? Do you want to take off one of the extra cameras? Do you want to go to 4 wheels instead of 6? What? Tell me what to take off. And we're like, really? Well, how long will it last if we don't put wipers on? How long will it last if we don't put a spray can of air on to clean their panels off? Well, it'll last at least 90 days on Mars. And that's your primary mission. That's what NASA says you get for your primary mission. You achieve your science goals in 90 days on Mars. And the panels will collect dust and the power will go down, but you'll last 90 days. And we said, do we want to make that trade? Throw off the spare transmitter, throw off a redundant system. We decided not to make that trade. We said, okay, you say it's going to last 90 days. We need to last at least 90 days. And then, what happened? Of course, 120 days in, the power is getting lower and lower, and we're 200, 300 sols in, we're getting lower and lower. And then we climb the hills, and what happens in the hills? Wind, right? Clears the, like the questioner asked. We got lucky, and boom, power jumps up, and you got a new lease on life. And that happened multiple times with both vehicles that were solar powered. And so, not an obvious answer to a great question.
Okay, and so I'm going to cheat a little bit here and interject my own question real quick. You several times you said sols, right?
Yeah.
Compared to days on Earth. Could I ask you to clarify that for folks?
Yeah. So Earth spins on its axis once per day. That's the definition of a day, right? Mars spins once on its axis once per sol, S-O-L, kind of named after our star, Sol, the sun, right? And the reason it's not a day is because the length of time is different. It takes Mars 40 minutes longer to spin once on its axis. So it's 24 hours and 39 and change minutes instead of 23 hours and 56 and change minutes that the Earth has, right? So it's a little bit longer every day. And so it has to have its own name because it's different than a day. right? And for a while, all these missions, we were living on Mars time, especially for the solar powered missions, because what matters is when the sun rises and sets, not what time it is on the Earth, right? So if the sun rises and it's noon on the Earth, today it sun rises on Mars at Gusev Crater. Tomorrow the sun rises at 12:40 p.m. And the day after that, the sun rises at 1:20 p.m. And the day after that, the sun rises at 2 p.m. And it's sort of slowly clicking through the day. And after a couple of weeks, we're working in the middle of the night because that's when the sun rises, right? And so we had to stay on this screwy Mars time schedule, and we were studied by sleep therapists, people who study folks who work in nuclear submarines and have totally weird clues to their circadian rhythms. And it was kind of cool, but it kills you. It kills you to be not on the circadian rhythm that we are evolved to be on. It's just everybody gets sleep deprived and cycles off, and you get irritable, and people start making mistakes. So after about 3 months and change, they brought us all back to the Earth. They put us on Earth time. And so we clock through the Mars day while we can on normal Earth hours. And then we have to, basically plan a couple of days in a row because we're flipping through, we're waiting for Mars to come back to the normal Earth daytime. It was less efficient, but we're not killing each other and breaking the spacecraft. So.
Right, that human element.
Yes, because you've opened the door. I can't help but volunteer this, right? It's like a lot of people out there think the robots are exploring Mars. We push a couple of buttons and the robots go do these things and then send us, this information back, and we think high thoughts and write papers. It's not. The robots are tools, right? I mean, this is a blasphemous thing to say, but they're not even as smart as a toaster, right? They're about toaster smart, right? They're as smart as their software. They do what they're told. They are machines. They're tools for people who are exploring Mars through these tools. So to me, it is human exploration. We're just not there.
Right, and I guess that calls back to what you were saying earlier about avatars.
Yeah, exactly.
So speaking of, there's a few more questions about the tool. So Thomas was asking, has it been thought of using a light gas like helium in a blimp instead of the helicopter model?
Yeah, I've seen ideas pitched for that. There's no reason why it wouldn't work, especially if it's tethered. You could tether it to the rover or the lander. And balloons have been used on Venus, in the Venus atmosphere. So there's, rich heritage of materials and, processes to inject gas into inflatables in planetary exploration. So yeah, it could be done. I think, maybe not as much mobility. Maybe you're more subject to the whims of the wind than if you have the power of controlled flight and the precision of controlled flight that a drone has. But I'm sure people have thought about it in detail, and there'd probably been proposals submitted that just haven't been selected yet to do something like that.
Okay, and then one more question related to Ingenuity. Do its blades auto-clean its solar panels?
No, unfortunately. The solar panel is above the blades. And so the flights appear to be keeping the panels pretty clean because, of course, it's moving through and it tilts a little bit as it's going forward. And so there's a breeze going across those panels. But still, they are getting dusty. It's electrostatic, right? Attracting. The dust is smoke size. Sticks to everything. It's going to be a huge problem for people and machines and your space suits and all that, seals, all that kind of stuff. But no, there's no active way to intentionally clean those panels. But like the rovers themselves, the lifetime of Ingenuity was supposed to be shorter than it already is. So the flights and maybe the wind and just the generally less dusty environment in Jezero compared to a place like Gusev is helping that vehicle stay power positive.
Got it. So continuing the tradition of outlasting the warranty. And so a question from Mel. asking about sort of the balance between how much are the rovers autonomous versus manually controlled? I mean, there's going to be a delay in giving commands.
Right. There's no joysticking. We are never in joystick manual control of these vehicles. They're too far away. And so everything is sent to these vehicles as like a long to-do list, time tagged. Drive 3 meters forward, turn 20 degrees, drive 10 meters forward, put the arm out, drill into this rock. It's just a long time tag series of commands. Take pictures, move the mast, et cetera, et cetera. Within that set of commands, some activities are relatively autonomous. We can put it in a mode where we tell it, or you're at XYZ position here, you want to get to that XYZ position, you've got a map on board, go. Avoid obstacles along the way. If you're not sure if it's an obstacle, stop, phone home, right? Pretty simple autonomy, but we get more range out of the vehicle. We get often farther than we would have if we just drive to where we can see in yesterday's pictures, right? We can get farther that way. The whole sample processing, once we collect that core, it goes into the rover. It's entirely autonomous. There's no ground in the loop at all. It collects the core, spins it into the rover. That little arm grabs it, moves it from station to station where it's documented, sealed, and then placed very carefully into its tray. That's all automated. So you basically just tell it to command, take sample, boom, goes and does that. So Perseverance is the most autonomous of all of them so far. But at the end of the day, they are really following instructions which are carefully choreographed based on what people have seen in yesterday's data. And so there's a lot of tactical reactions. We might have a strategic plan and we think we want to go over there. And the tactical reality on the ground is, whoa, look at that. We've got to stop. And again, we've seen examples of this, having a strategic plan and throwing it out. Kind of the military people probably recognize this, right? The tactical reality on the ground is totally different than what you had planned strategically. And the team is nimble and we can respond to that if needed. Or lots of times maybe we're just driving and it is relatively routine and we are following a strategic plan. So lots of different layers to the operations, but all of which involve people making decisions as a group. Hundreds of people, about 500 people on the science and operations team for Perseverance, for example. Hundreds of people interacting virtually like this, like we're doing every day in meetings and, poring over images and other data sets, making tactical decisions, feeding those into the plan as a group.
Wow, never gets lonely, sounds like. So with the
pretty exciting, yeah.
So related to the sampling that you just brought up, several people asked about this. So where will Perseverance place its sample containers? Just one location, or will there be some redundancy of doing several stashes?
Great question. We don't know the answer. This is going to be, this is an evolving plan. It's going to depend on where we collect samples, how many we collect, where the sample fetch rover and lander are going to be able to go. We don't know that yet. And so lots of unknowns. And so, for now, we're focused on collect that cache or caches. The fact that we're collecting two in many places means that we could split it and do it in two different places if we want, or we could send double samples back in the cache, the first cache that we place, TBD, do not know. Lots of decisions yet to be made, and lots of information we don't have yet to make those decisions.
Right. So TBD, got it. And so now going into some questions about the science. So I've got a question from Mike asking, where did the water go? Is there any water left?
Yeah, great question. Where did the water go? So, some of it's still there. Mars has polar caps. Water ice is there. Some of it is buried in the subsurface at high latitudes. The Phoenix lander scraped the surface and exposed that water ice just under the dusty surface at high latitudes. So there's a bunch there still. on the surface seasonally as polar caps and in the shallow subsurface. But that's not enough to explain what we think was a much more watery history. Some of it could still be there underground, deeper underground in aquifers and groundwater systems, especially closer to the equator where it's warmer. But one of the goals of another mission, a sister mission called MAVEN, was to answer this question by studying the upper atmosphere. And one of the main results that came out of the MAVEN mission, basically proving the hypothesis that because Mars doesn't have a magnetic field, the solar wind is interacting with, pounding into the Mars upper atmosphere all the time, knocking hydrogens off of H2O. And the hydrogen escapes, the oxygen goes into CO2 photochemistry and oxidizing the rocks. But you lose water that way very slowly. It's been measured by the MAVEN mission. Can measure today the amount of water being lost from the upper atmosphere because of the solar wind. And if you go back in time, you take that rate and go back in time 1 billion, 2 billion, 3 billion years, you lose a lot of water. And so much of the water that Mars had has been lost to space as it goes back and forth between the atmosphere and the surface. Once it gets into the atmosphere, broken down by the solar wind. Some of it's still trapped there. We don't know how much, but much of it lost to space over time.
Okay, so then another question related to chemistry discovered on Mars. So Seth is asking, with the discovery of carbon compounds on the surface of Mars, has that led to have the Viking biology experiments needed to be reevaluated? So I'm not quite sure which experiments are being referred to here, but
yeah. So the Viking experiments was the first organic chemistry experiment on another planet back in the late 1970s. They found evidence for simple organic compounds. We know that they're delivered to Earth and Mars all the time by meteorites, by comets and asteroids, which many meteorites have simple organic compounds. Not the kind of compounds that are complex biologic DNA molecules, et cetera, but simple precursors were found, have been also found by Curiosity, its organic chemistry experiment. So in a sense, Curiosity brought experiments to kind of rerun parts of some of the Viking experiments and found similar results, extremely minuscule amounts of organic material on the surface. But some of it, the kinds of precursors to the organic chemistry that we and life on Earth are made of. No, life-like molecules discovered, but maybe we shouldn't have expected that. We didn't know a lot about Mars when Viking did its experiments. We didn't know about how bathed in ultraviolet radiation the surface was. We didn't know that there are these materials called perchlorates that break down organic molecules in the soil, right? That was discoveries made by later missions. So there's a lot of reasons why Mars shouldn't have complex organic molecules right on the surface. What we don't know is what's underground. Get down below the harmful ultraviolet radiation. Get down below the areas where the chemistry of perchlorates can break down organic molecules. Get down where it's warmer. Get down where maybe there's a water table. Maybe there's complex organic molecules down there. We have to figure out how to access the deeper subsurface on Mars, and future missions are going to try to do that.
And so with the current mission where samples are being collected, if any apparent fossil or biological evidence is observed in the rocks that are being cached, what adjustments will be made for returning those samples to Earth? Will there be a biosafety lab built to handle and test the return to Martian materials?
Yeah. Well, first of all, there'll be a big party, right? Because it'd be one of the most incredible discoveries in the history of history, right? So, okay, after the party, then we need to think about what do we do? And in fact, the plans are that when this material comes back to the Earth, they will be treated very, very carefully, because we don't want to contaminate that stuff with Earth life, right? We don't want to discover life on Mars in a sample because something in the laboratory crept in, right? And so they have to be kept super clean super sterile relative to the environment outside. And it's, similar to conditions that we handle moon rocks, for example. They're in very carefully climate controlled laboratories. Some of the Apollo samples still haven't been opened, right? They're still waiting for advances in technology to go in and look at some of the samples. So yes, they will be handled very carefully, not because we think they're going to pose a threat to us. Andromeda strain fans might be thinking about that, right? But that's not really what the concern really is, the scientifically based concern. It's really about us contaminating them. It's about us searching for evidence of life, or the precursors of life, or the materials of life in these samples, and not wanting to rediscover Earth life in the process.
Make sure it's really Mars life we're finding.
Yeah.
So, yeah. Okay, all right. So now going into a set of questions related to the future, so future work. So one idea somebody asked about is since the helicopter has been able to be used to blow Martian dust on purpose, could a helicopter be paired with another future rover and use the helicopter to clean that one's solar panels?
Why not?
Hovering above it?
Absolutely. There's no reason why not. Okay, why not? It's risky, right? Things flying around, the wind could gust it, could crash it into the rover. Okay, so if you can figure out how to control the risks, why not? It's a great idea. If those future rovers or landers or whatever are solar powered, having some way, we know from experience that Mars dust is a killer, right? Mars dust kills solar powered spacecraft in the atmosphere by blocking out the sun, on the surface by covering the solar panels themselves, on the surface by creating these dusty piles that we get bogged down in, right? So many ways that Mars dust kills rovers. So whatever mitigation can be done, if a vehicle is solar powered, yeah, go for it. Test it out in the laboratory, mitigate the risk, fly it.
Great. And then just more generally, Anne's asking what design improvements will be built into the rovers that are following?
Yeah, that's a great question. So, clearly there has been an evolution of capability, more autonomy, more ability to do onboard processing and onboard interactions with the environment, to get greater range, to select samples, to process samples, to process data, whatever. We need more bandwidth on Mars. I think that's coming. More orbiters at higher communication rates. We barely have dial-up to Mars, for those who remember what dial-up was. I think you guys remember what dial-up was. Maybe people, what's dial-up? Go look it up. It's in the Smithsonian, right? We barely have dial-up rates. There's not high-speed internet, right? And that's a limiting factor. We can only send so much data back. We can take hours and hours of movies and all kinds of data, but we can't get it back to the Earth. So it's why would we do that? So advances in communications technology and bandwidth, that's coming, and more sophisticated instruments with greater sensitivity, miniaturized laboratories as all of space exploration is getting miniaturized, and the small sat revolution that's happening now in space exploration and commercial space. All that's going to trickle into NASA missions as well. So lots of engineering advances, and we're getting smarter scientifically too. We're learning more about the planet and the places to go, and other planets, other places to go, where we can try to pinpoint those questions, many of which are centered around life elsewhere in the solar system, life elsewhere in the galaxy.
All right, well, going into the final two questions here. So just a couple more questions here. We got Naomi asking, who gives the final say to decommission a rover or drone? Is it NASA or the researchers?
Yeah, NASA, I don't know if there's actually a death certificate, but NASA, if there is, would be the ones to sign it. Of course, we try every single one of these, we try to continue communicating, try different contingencies, and, follow, a whole set of assumptions. Well, maybe this happened, maybe that happened, and we'll listen at this frequency, or we'll listen at this time. And so pretty heroic efforts are made to get back in communications. And a number of spacecraft have been saved by those heroic efforts. The Spirit rover died only a couple of weeks in, just before Opportunity was coming in, because of a software bug, basically, that wasn't discovered because there hadn't been enough testing on the Earth. But it was saved by super clever people who were thinking of every possible contingency. And one of those contingencies was actually the one. And they figured it out and they brought it back to life. So just because it's not talking today doesn't mean it's not going to be talking tomorrow or next week. But eventually, after weeks and weeks of efforts, and you follow all possible failure modes, they call them, and if you are not successful, then that's declared by NASA the official end of the mission.
All right, and now we'll have our final question for the evening. Again, I would like to thank all the people who've emailed in. Sorry, we can't get to everybody's questions here. But we've got a question, somebody asking, do you think that there will ever be a permanent scientific base on Mars, similar to like how we have a base at the South Pole?
Absolutely. Absolutely. I have no doubt. Look, if you haven't figured out I'm an optimist by now, you're never going to, totally. This was the Andy, you mentioned the Ultimate Interplanetary Travel Guide. The premise of that book was it's 200 years in the future, and you need sort of like a Foder's Guide or a Lonely Planet because you want to go to the moon for the weekend, or you want to go to Mars for the summer, or something like that, right? And that was, I was guessing 200 years from now, that might be a reality. It took 100 years to get to the aviation industry and on the Earth, where you can go almost anywhere on our planet in a couple of 2-3 flights, right? It took 100 years to do that. Maybe it'll take a couple of 100 years and we'll go anywhere we want in the solar system. And scientific research will be driving a lot of that. Tourism will be driving a lot of that. Eco-tourism, science, helping scientists as tourists. We see that on the Earth already. You can go to Costa Rica and work in the rainforest, whatever, right? I think that's coming out there in the solar system as well. And so, I tell people, especially young people, eat well, exercise, live long, and maybe you'll get to go to the moon for the weekend on your 50th birthday, your 75th birthday, your 100th birthday, whatever. But absolutely, a base, cities, settlements on the moon, Mars, asteroids, other places in the solar system. It's all coming, and I'm super excited about it. I'm super optimistic about it, but I also can't wait. It's going to be great.
Well, thank you so much, Dr. Bell, not only for sharing the science, but for sharing the obvious relish you have for your job. And may your vision of the future come true. We really appreciate all the information and all the ways in which you've made us see Mars come alive before our eyes. This concludes this particular lecture in the Silicon Valley Astronomy Lectures, and we are at the end of 2021, but we will be back in February 2022 and several more times during the spring of 2022 with more lectures. So stay tuned and check often with the YouTube page on which you're watching this. Thank you, everyone. And on behalf of all the sponsors, good night.